In this video, we would like to talk about a very hot topic in multimedia technologies, that is image impainting. We will have a very brief introduction first, and then we will describe OpenCV and Photoshop image impainting technologies. And then we will describe context encoder in deep learning technologies. In this part, we will have a very brief introduction. So what is image impainting? Impainting is the process of reconstructing lost or deteriorated parts of images and videos. It is previously done by artists, and now it should be done by computer programs automatically. So let's give a problem formulation. Given images that the destroyed parts is non-detectable, our goal is the modification of images in a way that this is non-detectable for an unknown observer. There are many kinds of applications in image impainting technologies. For example, it can be used to restore the damaged photographs. It can be used to remove undesired objects and writings on the image, such as removing red eye, logos, and etc. And it can be used to replace the lost blocks in the coding and transmission of images. And actually, there are many methods to do image impainting. And image impainting is a very hot topic in research area. So in the following parts, we will describe 3 different methods to do image impainting, and let's see how things go on. In this part, I would like to talk about image impainting in OpenCV, a very famous open source computer vision library. And there are actually 2 implementations, and I would like to just talk about the implementation by Teller, and all can be found in the documentations of OpenCV. The algorithm to be described are actually in 2 steps. The first step, we use fast matching method to find the closest point P in the missing area, and there must be some closeness measures, and iteratively we process to fill the whole region. And after we find that point P, we use known points in the neighborhood of P to impaint it. So the contexts here are actually the known points, and we use a normalized weighting function to estimate that point value. So the weights should be defined properly. Here are some definitions we should pay attention to: the region, boundary, neighborhood, the intensity of a point Q and its gradient. And we use first order approximation to calculate value of P in the Q's direction, and we use a weighted summation to calculate the whole value. So there is another question: how do we define the weights? Let's see, the left figure shows the missing area and its boundary. And for a single point P, we use its neighborhood B epsilon of P to calculate the value on it. And for the right figure, it shows the first order approximation. The algorithm we will describe here is quite straightforward and simple. After we find the boundary and the missing area, we use an iterative way to do it. First, we find a point P, then we impaint it, and we advance the boundary into the missing area until we finish all the things. The fast matching method tries to solve Equinol equation. In this formula, T is the distance map of pixels to the boundary, and delta T is the direction n to the boundary, and is also called the isoforce direction. The fast matching method guarantees that the pixels in the boundary are processed according to the ascending order of T. So the closest pixels up to the known areas are always processed first. So how do we calculate T? The algorithm shows an elegant way to process the boundary, and is called a narrow band. The narrow band separates known points from unknown points. For each pixel, we compute the following values: the T value, the intensity, and the flag shows the point's position. And the narrow band is maintained by the min heap, so that the algorithm with the minimum T will always process first. Let's see how the algorithm works. For the points in the narrow band, in step 1, we extract the head, which is the closest to the boundary, and we find its neighbors. And in step 2, we update its flag, and in step 3, we impaint it, and in step 4, we calculate the T value. And the last step, we insert the point to the narrow band until we finish all the points in the narrow band, and the algorithm finishes. The algorithm here shows an elegant way to calculate T by solving the bottom equation. As we previously described, we need to define the weights properly to impaint the point. The weights here are multiplied by 3 components: the direction component, the distance component, and the level set components, and all this contributes to the final value of P. Here are some experimental results. The impainting mask in figure B is actually the damaged part in the original image in figure A. Compared with previous results in C and E, the method in OpenCV shows relatively good results. Let's see another example. Look at the damaged face and the recovered face by this method. Generally, this looks good, but if we zoom in, we can still see some artifacts in figure J compared with figure I. This is due to a blurring effect. If we want to recover the image by detail, this is not good enough. At the time the algorithm was first introduced, it is a relatively good algorithm and it shows several advantages. It is simple to implement, and is fast enough to handle different kinds of images in a very short time. Compared with previous methods, it shows similar results, and the algorithm can be customized to use different local impainting strategies to handle different kinds of images, so it can solve many kinds of image impainting problems.
Alright, let's move on. The next part, I would like to talk about patch match. Image impainting is the process of reconstructing missing parts of an image. The key question is, how could we fill these missing parts by only using the input image? For example, in the photo on the left, the missing parts are the holes on the building, and the photo on the right is what we expect as a result after impainting. To do this, we could use the patch match algorithm. It is an algorithm to find the similar patches in the image. Once we get the most similar patches, we could perform the impainting by taking advantage of these patches. However, finding these patches is not an easy task. In earlier studies, most of the method is a kind of naive approach. That is to search for all patches in one image region to find the most similar one. The problem of this method is it spends too much time in searching. The cost of computing a field of such matches for an entire image is so hard that makes it impossible for large images. Fortunately, the researchers found out a new method which is called randomized algorithm. The aim of this algorithm is to quickly find out the approximate nearest neighbor matches rather than all patches. The randomized algorithm offers substantial performance improvements over the previous studies, making it possible to apply them in even large images. The new algorithm relies on three key insights: the dimensionality of sight, the image's natural structure, and the law of large numbers. The dimensionality of the patch space is large, but it is sparsely populated. The new algorithm takes advantage of this idea to search in a 2D space of possible patch offsets instead of search in the whole space. And the natural structure of the image is the second idea. The Euro-independent search for each pixel ignores the natural structure in image. However, the neighboring pixels usually have coherent matches. Thus, we can improve efficiency by performing searches for adjacent pixels rather than all pixels. Finally, the law of large numbers. Whereas it is very unlikely to be a good guess when we made a random choice of patch assignment, a large number of random sampling, however, will likely to be a good guess. As the number grows even larger, the chance that no patch will have a correct offset becomes very small. Based on these three observations, the randomized algorithm has three steps: initial guess, propagation, and random search. The first step is initialization, where each pixel is given a random patch offset as initialization. Then, propagation. For each one of these pixels, check if the offsets from its neighboring patches could give a better matching patch. If so, we adopt the neighbor's patch offset. The last step is random search. In this stage, we enlarge the search field. For each pixel, we search for better patches within a concentric region around the current offset. As the search goes on, we reduce the search radius step by step and get back to the original offset eventually. Image compilation of large missing regions is still a challenging task. Even the most advanced global optimization-based method can still produce inconsistencies. where structured content is imprinted. For example, the imprinting process may break a straight line when it crosses the missing region. However, in the new algorithm, it was designed to be used together with constraints to improve the result, like the guided structure propagation approach. For example, let's look at the input image. We want to remove the bird from the input image. After removing it, we could draw lines across the missing region to define where they should pass through it. In this way, the algorithm will automatically follow these rules to do imprinting without cause any inconsistencies.
In this part, I would like to introduce a measure of image imprinting using so-called context encoder. Well, generally speaking, it is an unsupervised visual feature learning algorithm driven by context-based pixel prediction. And the most important innovation point of this measure is the use of context encoder. The context encoder is actually a convolutional neural network trained to generate the contents of an arbitrary image region conditioned on its surroundings. And the work it mainly does consists of two parts. Firstly, to understand the content of the entire image, and secondly, to produce a plausible hypothesis for the missing parts. Now let's look at the structure of the context encoder. It can be seen as a simple encoder-decoder pipeline. Firstly, there is an encoder. It is used to capture the context of an image into a compact latent feature representation. Secondly, there is a decoder, which uses the representation to produce the missing image content. Finally, there is a channel-wise fully connected layer connecting the encoder and decoder, and intending to propagate information within activations of each feature map. And now we can see the schematic diagram. The image with the missing parts is the input data, and it is processed by the encoder and get the encoder features. The features are then passed by the channel-wise fully connected layer and become decoder features. The decoder uses these features and finally generates the missing parts. And this is the schematic diagram of the encoder. We can see that there are 5 convolutional layers. The operation the convolution layer does is convolution. The feature it finally gets contains some deeper semantic understanding. Well, this is just the hard task the encoder intends to solve. To fill in large missing areas of the image where it cannot get hints from nearby pixels, thus requires a much deeper semantic understanding of the scene, and the ability to synthesize high-level features over large spatial extents. Now we can see the structure of the decoder. Well, it is nearly the reverse version of the encoder. While the convolution operation is replaced by unconvolution, the decoder uses the feature to generate the missing parts of the image. And the up convolution is the reverse operation of convolution, which results a higher resolution image. It firstly reverses the convolution kernel in both the vertical and horizontal direction, and then adds a 0 behind each element of the result of convolution, according to the step. After padding the result of convolution with 0, do the convolution with the reversed convolutional kernel. Now let's see the loss function. The loss function is important in CNN. Well, the machine learning can be seen as a kind of optimization problem, and the loss function is a cost which it wants to minimize during the learning period. In this particular problem, because there are multiple equally plausible ways to fill a missing image region which are consistent with the context, the loss function is used to handle both continuity within the context and multiple modes in the output, and thus consists of 2 parts. Firstly, the reconstruction loss. It captures the overall structure of the missing region and coherence with regards to its context, but tends to average together the multiple modes in predictions. Secondly, the adversary loss, which tries to make prediction look real, and has the effect of picking a particular mode from the distribution based on generative adversary network, the GAN. And in this diagram, we can see the 2 loss functions. Now let's see the adversary loss. Well, it is based on GAN. The GAN always has 2 models, the generative model G and the discriminative model D. The learning procedure of GAN is a 2-player game. D takes in both the prediction of G and ground truth samples and tries to distinguish them, while G tries to confuse D by producing samples that appear as real as possible. When D cannot distinguish the image G generated from the real image, the learning stops. And this is the experiment result. We can see that it can generate the missing parts as real as possible.